4.2. Today we're going to be talking about summation notation right here. You might have seen these mathematical symbols before. It looks like a Greek letter, and some people call it sigma. So another name for this is actually sigma notation. And essentially, sigma just means sum. So literally just add numbers together. The way it works is this bottom thing is called an index, and it tells you where to start. So think of that as your starting number. So start at this number. This n at the top tells you where to stop. So stop when I is equal to n. So to model this, let me show you a couple examples here. So you start at the bottom, I equals 1. So plug in 1 there, you get 2. Now plug in 2, that's 5. Now plug in 3, that'd be 10. Now plug in 4, that'd be 17. Plug in 5, that's 26. And then plug in 6, and you get 37. And I'm going to stop here because it says stop at 6 right here. So now we just add them all together, and you're going to get 97. And that's your answer. So let's go to B. It's a start at 4. So plug in 4. That would be 16 minus 5, which is 11. Now plug in 5. That's negative 32 minus 5. That's negative 37. Plug in 6. That's 64 minus 5, which is 59. Now plug in 7. And that would be negative 128. So negative 133 is your final answer. Now add them all together, and we get negative 100 as your answer. Now for the final one, notice on this one's kind of unique. There's no variable here. So that's interesting because that means if you plug in 1, you get 3. If you plug in 2, you get 3. If you plug in 3, you get 3. And you stop at 5. So all you have to do is simply think, well, what's 5 times 3? And that would be 15. Okay, let's try this checkpoint right here. So you can try this on your own, or you can just do it with me. I equals 4, you get 3, dot, 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 all the way to I equals 17, you get 3. So the real question is, how many 3's are there? Now, make sure you're aware that to figure out how many numbers are between 4 and 17, you do 17 minus 4 plus 1. So that's going to create 14, which means there are 14 3's, and the answer is 42. Now you might be wondering, why is there a plus 1? Well, think of it this way. From 1 to 10, there are 10 numbers, right? So just think 1 to 10. If you simply do 10 minus 1, you get 9. So what's happening is it's counting all the numbers from 10 to 1, but it's not counting that first number. So that's why you have to add 1 at the end, and you get back to 10. Okay, let's do B. K equals 0, and then you get n, dot, 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 k equals 10, and you get n. So this is kind of like the last problem. It's a question of how many n's are there, and in this case, there would be 11, because there are 11 numbers from 0 to 10. Now for our last problem, 3x from 0 to 5. So hopefully we can do this a little quicker now. So that would be 6 times 3x. And then from 19 to 9, that would be 11 numbers. So 11 times 2. So 18x plus 22 must be your answer. Now to our final part. Now we're going to go backwards because it says write each of them in summation notation, which means we want to write it in that form right here. Now to make this easier, you're going to want to use 1. That's going to be a typical easy number to think about. So start by just writing this. Now think about the formula. So look right here. Notice how this 3 is there every single time, which means you definitely need a 3. And the thing that's changing is what the index is doing. So you want to look at right here. So that means it must be I cubed, because if you plug in 1, you get this, 2, 3, and we can see we stop at 7. So we're good. B, a little bit harder now. So start by just writing 1. This one, notice how there's a variable at the end. So this thing is your last term. We don't know what it is, so we want to just call it the nth term. And a really easy way to do this is basically grab this thing and plug it in right there. Except instead of writing n, you change the index to I, which is what this is. Because by doing that, you just make it end at n, and you're going to see that it matches it perfectly. Because now if I plug in n to this, I get this, which is great because it's stopping here. If I plug in 1, I get 3 to the 0, which is 1. If I plug in 2 here, I get 1 over 3, so it checks out. So again, that's a really easy way to do something like this. Basically grab this last term and plug it in right there and fill in an n. Now here's our last example here. We're going to put I equals 1. And this is kind of tricky, so we're going to kind of think about a formula that can fit this. I'm going to notice it goes up by 2 every time, which means I definitely need a 2i in there. But if I just plug in 1, I get 2. So to balance it, I'm going to have to put a minus 1. Now let's see if that works. If I plug in 1, I get 1. If I plug in 2, I get 3. Okay, so it looks like it's checking out. The only issue is this. Where does it end? So I'm going to do a quick check. 21 is equal to 2i minus 1. So 2i is equal to 22. So I must have been 11. So there's our answer. Now, we're going to do one more thing. I'm going to show you how. So theoretically, you can do an infinite number of answers here. Now, I showed you that 1 is a really easy place to start. The other index that's really helpful is 0. So plug in 0 right there. Now, what you can do is if you make this 0, this 7, that should also go down 1, right? Because notice the index, if we subtract 1, then this 7 should also go down 1 to 6. Now, what's tricky is the formula. If this formula is now going down in index, think about what's happening here. It has to compensate. So let's put, it must compensate. And by compensate, think like fix. So there's a minus 1 right here. So to compensate this thing, we need to put a add 1. And now the formula still works, because if I plug in 0, I get 1 cubed. I plug in 1, I get 2 cubed. Plug in 6, I get 7 cubed. So notice how these answers are linked, and you can use this answer to get the other answer, or really any theoretical answer. Let's try another one. We're going to start at 0. But again, notice how if this thing is going down by 1, this thing must also go down by 1. And that has to happen because you have to keep the number of terms the same. But to compensate, this index here, it must compensate. So now it's going to be 3i minus 1 plus 1, or let's erase that. The ones cancel, and you just get that, 3 to the I. Now for our last example, let's take a look if we can figure this out. So if I follow that same pattern, I'm going to drop it to 0, which means 11 should then drop to 10. And if I just compensate, let's put an arrow here. I'm going to compensate plus 1. Then this should be 2i minus 1 plus 1. These cancel. And we get this. However, this definitely doesn't work. If I plug in 0, I get 1. If I plug in 1, I get 2. So none of these numbers are matching, which means the compensation here failed. Which means we have to understand this a little more deeply. The compensation means you replace I with I plus 1. So really, to fix this, I should say 2 times I plus 1 minus 1. And let's see if that fixes it. Because now that's going to be I equals 0 to 10. And this would be 2I plus 1. If I plug in 0, let's check. Yep, I get 1. If I plug in 2, if I plug in 1, I get 3. Okay. If I plug in 10, I get 21. So this does, in fact, work. Okay, so that was a quick lesson on how summation notation works. If you have any questions, let me know.